How to achieve high-fidelity Transmon Qubit Readout. Imagine trying to hear a whisper in a noisy room. That's similar to reading a qubit state accurately in a quantum computer. Achieving high-fidelity readout means getting a clear, reliable signal every time. Transmon qubits are superconducting devices that are widely used in quantum computers. They are connected to a readout resonator, which acts like a tiny echo chamber. When you send a microwave signal into this resonator, the qubit state slightly shifts its frequency. By measuring the reflected or transmitted microwave signal, you can figure out if the qubit is in the 0 or 1 state. To make this process more precise, one key step is to increase the strength of the interaction between the qubit and the resonator. This is called dispersive coupling. When this coupling is stronger, the frequency shift caused by the qubit state becomes larger and easier to detect. For example, using a special device called a quarton coupler can boost this interaction from about 10 MHz to over 200 MHz. This allows measurements to be completed in about 5 nanoseconds with more than 99% accuracy. Plus, it keeps the qubit intact, so you can measure it multiple times without destroying its quantum information. Another important technique involves amplifying the microwave signals without adding much noise. Josephson parametric amplifiers are used for this purpose. They can amplify the tiny signals coming from the resonator, making it easier to distinguish the qubit state with high confidence. This method can achieve single-shot readout fidelities around 98 to 99%. It also simplifies the setup by reducing the number of components needed, which is helpful when scaling up to many qubits. Reducing errors caused by the measurement process itself is also essential. Sometimes, the measurement can inadvertently excite the qubit or cause it to jump to an unwanted state. To prevent this, engineers carefully design the circuit environment, control the power of the microwave drive, and shape the pulses used for measurement. These steps help keep the qubit stable during the readout. Using advanced control techniques like reinforcement learning can further improve the process. These algorithms optimize the shape and timing of measurement pulses based on the specific device, reducing errors and speeding up the measurement cycle. Recognizing the nonlinear effects that happen during measurement, such as higher energy state transitions, helps in designing better pulse sequences. This prevents the qubit from accidentally jumping to unwanted states, which can lower fidelity. In the end, combining a strong dispersive coupling with efficient amplification, careful error mitigation, and smart pulse control leads to fast, reliable, and scalable readout of Transmon qubits. This is a vital step toward building practical quantum computers capable of error correction and complex calculations. Each of these improvements helps us get closer to the goal of highly accurate quantum measurements, making the dream of powerful quantum machines more achievable every day.